Welcome to the world of supervised learning, where machines learn to predict by studying labeled examples. From email spam filters to medical diagnoses, this fundamental concept in machine learning is the backbone of countless applications. But how exactly do we guide machines to learn from data and make informed decisions? By providing them with a roadmap of labeled examples that serve as their training ground. Think of it as equipping them with a treasure map, where each labeled example is a clue leading to the correct prediction. In supervised learning, the machine is the eager detective, piecing together patterns and insights to crack the code of the data it encounters. So, let's dive deeper into this fascinating journey of teaching machines to learn from our guidance and make predictions that shape our digital world. Welcome to Chapter 1, What is Supervised Learning? Imagine supervised learning as using flashcards to teach. Just like a student learning from a teacher, the algorithm learns patterns by studying examples with correct answers. It's like preparing for a test where you're guided with questions and answers. In supervised learning, there are two main tasks: regression for predicting continuous values and classification for predicting categories. For instance, regression helps predict things like house prices or temperature, while classification distinguishes between spam and non-spam emails or healthy and diseased cells. Supervised learning is all about training algorithms to make accurate predictions based on past data. Ever wonder how real estate platforms determine home values so accurately? They employ regression models, analyzing factors like location, size, and market trends. In the medical field, classification models sift through patient data to predict diseases and suggest treatments. And in your inbox, email services rely on classification to sift through millions of messages, separating spam from legitimate emails. Meanwhile, e-commerce platforms use your browsing history to curate personalized product recommendations. From predicting prices to diagnosing illnesses and filtering spam, data science is transforming industries in ways we never imagined. Linear regression, ever heard of it? Picture this: you've got study hours on one side and exam scores on the other. Linear regression swoops in to draw the line that best fits all those data points, minimizing the gap between the line and reality. Think of it like this: y equals mx plus b. In this equation, y stands for our prediction, m for the strength of our relationship, x for our input feature, and b for our starting point. By getting this line just right, we can forecast scores based on study time. It's all about finding that perfect fit. Linear regression is a powerful tool, but when should you use it? First, for making continuous predictions like tomorrow's temperature or quarterly revenue. Second, when you have a clear linear relationship between inputs and outputs, such as house prices increasing with square footage. And third, when interpretability matters, linear regression is transparent and easily explainable to stakeholders. Imagine confidently stating, each additional bedroom adds $25,000 to the predicted price. Linear regression, precise, transparent, and powerful. Imagine being able to predict house prices with just one key factor: square footage. In a suburban neighborhood, every square foot counts. For each additional foot, the price climbs by about $150. So, for a 2,200 square foot home, you're looking at around $380,000. This straightforward linear regression model serves as the cornerstone for more intricate analyses, showcasing the power of simplicity in making accurate predictions. In Chapter 3, we dive into logistic regression, a technique for classification rather than regression. It predicts the probability of something belonging to a category, always outputting a value between 0 and 1. Values close to 1 signal a strong likelihood of yes, while those near 0 suggest a strong likelihood of no. For instance, it can determine if an email is spam or not based on features like word frequency and sender info, or assess the probability of loan default using factors like credit score, income, and debt. This method aids banks in making lending decisions. In the realm of classification models, there are two key players: binary and multi-class. Binary classification simplifies decisions into two outcomes, like yes/no or pass/fail, effortlessly handled by logistic regression's single probability output. For instance, predicting customer churn with a 0.73 probability means they're 73% likely to leave. On the other hand, multi-class classification deals with multiple categories, such as flower species or customer feedback sentiment. Logistic regression can step up to this challenge using methods like one versus rest or softmax functions. Embrace the power of classification models, from binary basics to multi-class mastery. In Chapter 4, we delve into decision trees, powerful tools for prediction. Imagine making decisions like a tree grows, branching out with each question asked. Start at the root, the key question that separates data best. Then, split the data into branches based on responses, grouping similar characteristics together. Keep refining, asking questions until you reach leaf nodes where data aligns on a label. When new data comes in, follow the tree's path to make accurate predictions. Decision trees mimic human decision-making, offering an intuitive approach to data analysis. In a world of complexity, decision trees provide a clear and structured path to insight. Ever wonder how algorithms determine the best question to split data for classification? By evaluating features like credit score and income against thresholds, the algorithm aims to separate classes effectively. In predicting loan approval, asking "Is credit score greater than 700?" proves more decisive than "Is income greater than $50,000?" The former leads to a clearer distinction between approved and denied applicants. Remember, the key lies in selecting the split that offers the most significant separation. Ever wondered why decision trees are so interpretable? Picture this: a visual flowchart mapping out each decision branch, making the prediction process crystal clear even to non-techies. Each route from root to leaf spells out an explicit if-then rule. If credit score greater than 700 and income greater than $60,000, then approve loan. Plus, the closer a feature is to the top, the more weight it carries in predictions. This transparency is crucial, especially in regulated sectors like healthcare and finance, where explaining model predictions builds trust and ensures compliance. Understanding the why behind predictions? It's not just helpful, it's necessary. In the world of data science, Chapter 5 introduces ensemble methods, strength in numbers. Rather than relying on a single model, these methods harness the power of multiple models to boost accuracy and resilience. Picture this: just like consulting several experts for insights, combining diverse models offers a more holistic perspective. By uniting these varied approaches, the risk of any individual model's errors is significantly reduced. In essence, the collective intelligence of many often surpasses the brilliance of one. In the world of ensemble approaches, two stand out as popular choices for boosting model performance. First up is random forest, employing the bagging strategy by creating multiple decision trees trained on diverse subsets of data. Each tree contributes its vote, resulting in a majority decision for classification or averaged predictions for regression. This method effectively combats overfitting, providing stability and accuracy beyond what single decision trees can achieve. On the other hand, we have gradient boosting, utilizing a sequential learning approach to iteratively improve model performance by focusing on correcting errors from previous trees. This technique often leads to the highest accuracy on structured data, making it a favorite in competitive settings like Kaggle competitions. In summary, random forest and gradient boosting offer distinct strategies for enhancing model accuracy and stability, with each bringing unique benefits to the table. Ever wondered how a single decision tree stacks up against ensemble methods in classification tasks? Combining models significantly boosts accuracy, although it may sacrifice some interpretability. The trade-off is often justified, particularly in critical areas like medical diagnosis or fraud detection. In these high-stakes scenarios, accuracy gains from ensembles can make all the difference. The power of collaboration in boosting accuracy is undeniable. So, while interpretability may take a back seat, the results speak for themselves. In the realm of high-stakes applications, the choice is clear: accuracy prevails. In the delicate dance of model building, understanding bias and variance is paramount. Bias, or underfitting, occurs when a model oversimplifies, missing crucial data patterns. Picture fitting a straight line to curved data, systematic errors abound. On the flip side, variance, or overfitting, arises from a model being too complex, mistaking noise for signal. Imagine a wiggly line intersecting every point but failing with new data. Striking the balance between these extremes is key to creating robust models. Remember, avoid underfitting like the plague, and steer clear of overfitting's siren song. Ever struggled to distinguish underfitting from overfitting in your machine learning models? Picture underfitting as a novice, too simple to grasp the essence, resulting in low training and test accuracy. Now, aim for the sweet spot, just right, where the model skillfully captures the pattern without the noise, yielding high accuracy on both fronts. On the flip side, overfitting is like a show-off, overly complex and memorizing even the noise, boasting high training accuracy but stumbling in the test. Remember, balance is key. Seek that optimal fit for reliable predictions. Ever wondered how to tackle bias and variance in machine learning models? To reduce bias, consider using more complex models, adding features, or training for longer periods. To combat variance, aim for more training data, simpler models, and techniques like regularization and ensemble methods. Striking a balance is key. Finding the perfect model complexity minimizes errors on new data. So, how can we navigate this delicate trade-off effectively? By implementing these strategies thoughtfully, we pave the way for more accurate and robust machine learning outcomes. Ever wondered about the relationship between model complexity and performance? As model complexity increases, training error decreases, but test error follows a U-shaped pattern. Your sweet spot? Finding that just right level where both training and test errors are low, a sign of optimal generalization. Picture it like this: a model that's too simple struggles to grasp the pattern, leading to high errors all around. On the flip side, a model that's too complex overfits, getting lost in the noise despite nailing training data. Remember, balance is key in the world of model complexity. Ever wondered how machines learn to predict outcomes? In supervised learning, models analyze labeled data to make accurate forecasts. Linear regression and logistic regression serve as foundational tools, offering straightforward yet potent predictive capabilities. Decision trees, with their intuitive sequential decision-making process, provide a clear path to understanding complex data. Ensemble methods like random forest and gradient boosting excel by leveraging diverse model combinations to minimize errors. Remember, finding the right balance between model complexity is key to avoiding underfitting or overfitting. Strive for that sweet spot where bias and variance harmonize. Welcome to the final challenge. Let's put your newfound knowledge to the test with some quick concept check questions. 1. When do you choose linear regression over logistic regression? Consider the type of output you're predicting. 2. Why are decision trees known for their interpretability? Visualize and explain the decision-making process. 3. How do ensemble methods enhance single models? Think about the power of collective wisdom. 4. If a model excels on training data but falters on test data, is it high bias or high variance? How would you address this issue? 5. When faced with high training and test errors, should you simplify or make your model more complex? Beware of underfitting versus overfitting. You've mastered the basics of supervised learning. Keep refining your skills with real-world datasets to deepen your expertise. Remember, understanding is key to mastering any subject. Time to reflect on your journey, embrace the challenges, celebrate the victories, and never stop learning.